Hello, I am Giray, and I will be presenting our work, a deeper look into RowHammer's sensitivities, experimental analysis of real DRAM chips, and implications on future attacks and defenses. This is a DRAM module used as the main memory in many systems. A DRAM module consists of multiple chips, each of which contain multiple banks. Each bank is composed of multiple subarrays, and within each subarray, there is a two-dimensional array of DRAM cells. These cells are organized into rows that are selected using word lines, and the cells are connected to a row buffer via bit lines. This is a simplified diagram of a DRAM cell where the data is stored as capacitor voltage and accessed through the access transistor. A DRAM cell inherently exhibits several charge leakage paths and requires to perform refresh operations to restore the capacitor voltage with a time period called refresh window. To access a DRAM cell, the memory controller must first open or activate the row to fetch the row's data into the row buffer. The read and write requests targeting the row are serviced from the row buffer. And after all requests are serviced from the row, the memory controller must close or pre-charge the row in order to begin accessing data from another row. Due to an increase in cell-to-cell interference as a result of aggressive technology not scaling, rapidly activating and pre-charging a DRAM row can result in bit flips in physically adjacent rows. And continuing to access the same row results in even more failures in nearby rows. And this phenomenon is known as RowHammer. We refer to the rapidly accessed row as an aggressor row, and the rows containing bit flips as victim rows. RowHammer is a serious DRAM reliability and security problem. And denser DRAM chips are more vulnerable to RowHammer today. Understanding RowHammer is critical to find effective and efficient solutions. However, no rigorous study demonstrates how this vulnerability varies under different conditions. In this work, our goal is to provide insights into three fundamental properties of RowHammer that can be leveraged to design more effective and efficient attacks and defenses. These three properties are DRAM chip temperature, the time that an aggressor row stays active during an attack, and victim DRAM cell's physical location. In this study, we test 272 real DRAM chips of DDR3 and DDR4 modules from 4 major manufacturers. Based on our analysis, we draw 6 key takeaway lessons from 16 novel observations. Among these, we highlight that a RowHammer bit flip is more likely to occur in a bounded range of temperature if the aggressor row is active for a longer time and in certain physical regions of the DRAM module under attack. Based on our findings, we propose several improvements and show that our novel observations can inspire and aid future work on crafting more effective attacks and designing more effective and efficient defense mechanisms. This is the outline of the talk today. Let me begin with our motivation and goal. RowHammer is a serious DRAM reliability and security problem. Denser DRAM chips are significantly more vulnerable to RowHammer, such that the minimum activation count to observe a bit flip has reduced by more than an order of magnitude in less than a decade. Recent works have demonstrated that many defense mechanisms are becoming prohibitively expensive for future DRAM chips, and a deeper understanding of RowHammer is the key to overcome this challenge. However, no rigorous experimental study demonstrates a set of fundamental properties of RowHammer to find effective and efficient solutions. Therefore, to enable RowHammer safe operation with future DRAM chips, it is critical to gain insights into RowHammer and its fundamental properties. Our goal in this work is to provide insights into three fundamental properties: temperature, aggressor row active time, and victim DRAM cell's physical location. By doing so, we aim enabling research to find effective and efficient attacks and defenses. Let me quickly explain our experimental methodology. We use two FPGA-based experimental setups for DDR3 and DDR4 DRAM modules, both programmed with a modified version of SoftMC. We control the chip temperature using a pair of heaters connected to a temperature controller. These infrastructures provide us with fine-grained control over DRAM commands, timing parameters, and temperature. To characterize our DRAM chips at worst-case conditions, we take two measures. First, we prevent external sources of interference such that our tests can run consistently as desired and without interruptions. To achieve this, we disable DRAM refresh to avoid refreshing victim rows during RowHammer test, DRAM calibration events to minimize variation in test timings, and RowHammer mitigation mechanisms to ensure that we can directly observe circuit-level bit flips. We also ensure that our tests complete in less than a refresh window to prevent retention failures from interfering with our results. Second, we issue the worst-case access sequence for inducing RowHammer bit flips based on observation from prior work. Using these observations, we test each row's worst-case vulnerability to RowHammer by repeatedly activating the two physically adjacent rows as fast as possible. In our characterization, we test 272 real DRAM chips from 4 major manufacturers that implement the DDR3 and DDR4 DRAM standards, and with different densities, die revisions, and chip organizations. We provide more details about the chips we test in an extended archive version of the paper. Let's begin with our first analysis, temperature. This analysis provides two key takeaway lessons. First, to ensure that the DRAM cell is not vulnerable to RowHammer, we must characterize the cell at all operating temperatures. Second, RowHammer vulnerability tends to worsen as DRAM temperature increases. However, individual DRAM rows can behave differently from the dominant trend. We analyze the temperature levels the DRAM cell is vulnerable to RowHammer. We observe that there exists a lower and an upper bound of temperature, and a DRAM cell experiences bit flips only within this bounded range, but we do not observe any bit flips out of this range. We call this range vulnerable temperature range, and this table demonstrates the fraction of DRAM cells that experience bit flips at all temperature levels within their vulnerable temperature range. We observe that more than 98% of vulnerable cells across all 4 manufacturers exhibit this behavior. Therefore, we conclude that most DRAM cells are vulnerable to RowHammer throughout a continuous temperature range. This figure shows the population density of cells clustered based on their vulnerable temperature range. The x-axis and the y-axis show the lower bound and the upper bound of a DRAM cell's vulnerable temperature range. The color scale and percentage values show the fraction of cells for a given temperature range. For example, 0.4% of the cells are vulnerable to RowHammer only between 55 and 60 degrees Celsius. Similarly, 0.5% of the cells experience bit flips only between 70 and 85 degrees Celsius. From these observations, we conclude that different DRAM cells are vulnerable to RowHammer within specific temperature ranges. Here are the results for all 4 manufacturers. We make 2 observations from this figure. First, we observe that a significant fraction of vulnerable DRAM cells exhibit bit flips at all tested temperatures. For example, almost 30% of the cells from manufacturer D experience bit flips at all temperatures that we test. Second, we observe that a small fraction of the cells from all 4 manufacturers are vulnerable to RowHammer only in a very narrow temperature range. For example, 0.2% of the cells from manufacturer D experiences bit flips only at 70 degrees Celsius. Next, we study the impact of temperature on DRAM rows. The figure shows how the number of bit flips in the victim row changes as temperature increases. The x-axis shows the increase in temperature, and y-axis reports the variation in bit flip counts normalized to the mean value at 50 degrees Celsius. We observe that more cells experience a bit flip with increase in temperature. We repeat this analysis for all 4 manufacturers, and we observe that bit error rate increases with temperature in modules from 3 manufacturers. However, it exhibits an opposite trend in modules from manufacturer B. We hypothesize that this happens due to different characteristics of charge trap error mechanisms in different manufacturers. Please refer to our full paper for more details. Our main observation from this figure is that a DRAM row's bit error rate can either increase or decrease with temperature depending on the DRAM manufacturer. In the paper, we also analyze the variation in HC first, the minimum activation count at which a victim row experiences a bit flip. And we make 3 observations from this analysis. First, just like bit error rate, DRAM rows can show either higher or lower HC first values when temperature increases. Second, HC first tends to generally decrease as delta temperature increases. And third, delta HC first tends to be larger as delta temperature increases. Please refer to the full paper for these analyses. Next, we investigate the variation in RowHammer vulnerability with the time that an aggressor row stays active. This analysis provides two key takeaways. First, as an aggressor row stays active longer, victim DRAM cells become more vulnerable to RowHammer. And second, RowHammer vulnerability of victim cells decreases when the bank is precharged for a longer time. To perform this analysis, we conduct two sets of experiments. In the baseline, we hammered rows A and B as frequently as possible, while in the first set of tests, we increase the time that an aggressor row is active. And in the second set of experiments, we increase the time that the bank is precharged. This plot demonstrates how bit error rate varies when aggressor row active time increases. We observe that as the aggressor row stays active longer, more DRAM cells experience RowHammer bit flips. We observe the same trend on modules from all four manufacturers. In this plot, we investigate the variation in HC first, the minimum activation count, to observe a bit flip with increase in aggressor row active time. We observe that DRAM cells experience bit flips at smaller activation counts when aggressor row stays active longer. And when we repeat this test on all four manufacturers, we observe the same trends. So based on our observations on the bit error rate and HC first, we conclude that as the aggressor row stays active longer, more DRAM cells experience bit flips, and they experience RowHammer bit flips at lower activation counts. In the paper, we also investigate the variation in aggressor row active times effects across different rows and the effect of increase in bank precharge time. We make three observations from this analysis. First, as the aggressor row stays active longer, the RowHammer vulnerability consistently worsens across all tested DRAM rows. Second, as the bank stays precharged longer, fewer DRAM cells experience RowHammer bit flips, and they experience bit flips at higher activation counts. Third, the reduction in RowHammer vulnerability is also consistent across all tested DRAM rows. Please refer to the full paper for these analyses. Our third analysis is about the spatial variation. In this analysis, we investigate how the RowHammer vulnerability varies based on a victim DRAM cell's physical location. We have two key takeaways from this analysis. First, the RowHammer vulnerability significantly varies across DRAM rows and columns due to both design-induced and manufacturing process-induced variation. Second, the distribution of HC first exhibits a diverse set of values within a subarray, but similar values across subarrays within a DRAM module. To do this analysis, we first investigate how HC first, the minimum activation count to observe bit flips, varies across different DRAM rows, sorted by reducing HC first values on the x-axis. Each curve in this plot represents a different DRAM module. We observe that HC first values, and thus the RowHammer vulnerability, significantly varies across DRAM rows. The significant variation can be observed on modules from all four manufacturers. So to investigate more, we zoom into the most vulnerable DRAM rows, and we observe that the most vulnerable 10% of the rows experience bit flips at activation counts about half the HC first of the other rows. Therefore, we conclude that a small fraction of DRAM rows are significantly more vulnerable to RowHammer than the vast majority of the rows. To investigate how the RowHammer vulnerability varies across columns, we generate a heat map plot of bit error rates across columns and chips. We observe that bit errors concentrate on certain DRAM columns more than others, implying that certain columns are significantly more vulnerable to RowHammer than other columns. To further investigate the variation across columns and chips, we cluster each DRAM column based on its RowHammer vulnerability on average across DRAM chips and the variation in its vulnerability across DRAM chips. This plot shows the population density of DRAM columns exhibiting a level of RowHammer vulnerability and variation across chips. For example, 16.7% of DRAM columns exhibit a high RowHammer vulnerability across all chips, indicating design-induced variation across columns. In contrast, 30.6% of DRAM columns exhibit a high variation in their RowHammer vulnerability across chips, indicating manufacturing process-induced variation. Here we see the same analysis for all four manufacturers. We observe that there exist columns with very low or very high variation across chips from all four manufacturers. Based on these analyses, we conclude that both manufacturing process and design affect a DRAM column's RowHammer vulnerability. In the paper, we also analyze the variation across rows in a subarray and across subarrays in a DRAM module. We make two observations from this analysis. First, the most vulnerable DRAM row in a subarray is significantly more vulnerable than the other rows in the subarray. Second, HC-first distributions of subarrays within a DRAM module are significantly more similar to each other than those of subarrays from different modules. Please refer to the full paper for these analyses. Now I will explain the implications of our observations on future attacks and defenses. We believe that our observations can be leveraged to craft more effective attacks and to design more effective and efficient defenses. In the following slides, I will explain several examples for these implications. In the first example for an attack improvement, the attacker manipulates the DRAM module's temperature to increase the RowHammer vulnerability of the cells that store sensitive data. We observe that DRAM cells are vulnerable to RowHammer in a bounded temperature range that we call vulnerable temperature range. For example, let this range be from 50 to 70 degrees Celsius for the victim cells that we care about. To attack the cells within their vulnerable temperature range, an attacker can heat up the chip if its current temperature is below 50 Celsius, or cool down the chip if its current temperature is above 70 degrees Celsius. In the second attack example, the attacker uses RowHammer to understand the DRAM chip's current temperature. As an example, more than 76% of the vulnerable cells experience bit flips above 70 degrees Celsius for manufacturer C. Focusing on these cells, an attacker can identify abnormal operating conditions that might occur in a data center during its peak hours. By using this information, an attacker can trigger an attack when the data center is already under pressure. And if that is important to measure temperature precisely, the attacker can also focus on a smaller set of vulnerable cells that experience bit flips only in a narrow temperature range. For example, 0.4% of vulnerable cells experience bit flips only at 70 degrees Celsius in manufacturer C. Using these cells, the attacker can precisely detect the temperature and trigger an attack accordingly. In the third example, an attacker can leverage the effect of aggressor row active time. In this scenario, instead of activating aggressor rows as frequently as possible, the attacker can keep the aggressor rows active for longer time. And based on our analysis, HC first reduces by 36% on average with the proposed access pattern. And this is important because with this reduction, an attacker can bypass RowHammer defenses that do not account for this reduction. I will also explain two improvements for defense mechanisms in the slide, but you can find more in the paper. The first improvement leverages the variation across rows. We observe that 90% of the rows do not experience bit flips until the activation count reaches the double HC first of the 10% of the rows. Therefore, we can reduce the aggressiveness of defense mechanisms for these 90% of the rows. And this can reduce the area overheads of state-of-the-art RowHammer mitigation mechanisms, blockhammer and graphene, by 33% and 80% respectively. The second example leverages the variation in RowHammer vulnerability with temperature. We show that DRAM cells experience bit flips in bounded temperature ranges. And to avoid bit flips, a DRAM row can be disabled when its cells are vulnerable to RowHammer at the current operating temperature. We propose more defense improvements in the paper that I will briefly mention in this slide. First, leveraging the similarity across subarrays in a DRAM module can reduce the module's profiling time for RowHammer errors. Second, monitoring and limiting the aggressor row active time from the memory controller can reduce the RowHammer vulnerability and make defenses more efficient. Third, ECC schemes can target the non-uniform bit error distribution caused by design-induced variation across DRAM columns. And fourth, cooling DRAM chips can reduce overall bit error rate. Please refer to our full paper for more details on both attacks and defense improvements. To conclude, denser DRAM chips are more vulnerable to RowHammer, and understanding RowHammer is critical to find effective and efficient solutions. However, No rigorous study demonstrates how this vulnerability varies under different conditions. In this work, our goal is to provide insights into 3 fundamental properties of RowHammer that can be leveraged to design more effective and efficient attacks and defenses. These 3 properties are DRAM chip temperature, the time that an aggressor row stays active, and victim DRAM cell's physical location. In this study, we test 272 real DRAM chips of DDR3 and DDR4 modules from 4 major manufacturers. Based on our analysis, we draw 6 key takeaway lessons from 16 novel observations. Among these, we highlight that a RowHammer bit flip is more likely to occur in a bounded range of temperature if the aggressor row is active for a longer time and in certain physical regions of the DRAM module under attack. Based on our findings, we propose several improvements. We believe and hope that our novel observations will inspire and aid future work on crafting more effective attacks and designing more effective and efficient defense mechanisms. And this concludes my talk. Thank you for your time. I'm happy to receive any questions online or via email. We invite you to read our paper for many more details.